very much to Michael Bigman and all the people at Noise Within. We have really enjoyed this venue this year. I think it's marvelous, and I want to thank the audience for coming out. You guys have been terrific. So thank you to everybody. I think you'll see a lot of us back here. Thank you for your generosity. I also wanted to thank the Norris Foundation. Norris Foundation has been very generous in helping us to put on this lecture series this year. And it's my pleasure this evening to introduce Dr. Andrew Benson. And Andrew got his Bachelor of Science degree at Leicester in 1997. He got his PhD at Durham in 2000, and then he came across the pond to Caltech. And he was there for a few years before being drawn back to the UK, and he was a Royal Astronomical Society fellow at Oxford. Then he came back across the pond to Caltech, and unfortunately for us, he joined the Observatories in 2012. Andrew is an extraordinary young astronomer. He has made his mark in studying how galaxies form and understanding the role of dark matter in the formation of galaxies, which he will tell us about tonight. I'm not going to spoil his talk by giving a lot of the details about dark matter and some of the problems that he's worked on, but let me just say a little bit is that he really jumped into the field and worked on a number of outstanding problems where he's made really outstanding contributions to the field and our understanding of how galaxies form, how the halo surrounding galaxies is filled with dark matter, and how that has implications for the formation of galaxies. He actually started out when he was young wanting to do computer science, he told me, and then he got to university and discovered it wasn't as interesting as he thought it was, fortunately for us. Went into astrophysics and physics, and then discovered he could marry both of his loves and do computer science and simulations of galaxies. He's one of those fortunate people who really has gotten to do what he loves to do, and I think you'll see that in his enthusiasm. So I'd like to first, before I give the stage to Andrew, remind you to turn off your cell phones so that you can be undisturbed during his talk. And I invite Andrew to come up. And welcome.
Thank you. I'm good. I hope everybody can hear me okay? Yeah. We'll see. I have a mic on, but so we can ask the house to turn up the volume if necessary. So thank you, Wendy, for that introduction. And thanks again to all of you for coming out here tonight to hopefully learn a little bit about dark matter. So as you heard, I'm a theoretical astrophysicist, one of just a handful of us working at the Carnegie Observatories. My work is to try and understand what dark matter is and how galaxies in our universe form. And tonight I'm going to talk mostly about dark matter, but we'll throw some galaxies in there as well. And what you're looking at here, this beautiful image on the right-hand side of the screen, is actually a map of dark matter. It's what we think the distribution of dark matter looks like in our own region of the universe. So this would be sort of where our own galaxy, the Milky Way, is located, and our nearest galactic neighbor, the Andromeda Galaxy, will be somewhere up here. And hopefully about an hour from now, you'll have a good understanding of how we can actually calculate what dark matter is in the universe and what we think it might be made from. But before I do that, I want to explain to you why astronomers think the universe contains dark matter in the first place. Dark matter is, by definition, dark, so we can't see it, so how do we know it's there? So actually, some of the first evidence for this came about over 40 years ago now, and it came from Carnegie astronomer Vera Rubin. And Rubin was interested in understanding how galaxies like this one, which is a spiral galaxy rather like our Milky Way, she was interested in understanding how fast it rotated. So these galaxies are spiral shaped, they look like a flat disk of stars that are spinning around. And Rubin wanted to measure how quickly they were rotating. Now, why would you want to do that? If you've ever had the experience of tying a rope to a heavy weight and spinning it around your head, you'll know that you have to hold onto that rope pretty tight to stop it from flying away. And so in a galaxy, the stars are spinning around, and there has to be something to hold them together. If there wasn't, this galaxy would fly apart very quickly. And there are no ropes in galaxies, but in this case, what's holding it together is the force of gravity. The pull of the galaxy's own gravitational force keeps it in place. Now, gravity comes from mass. The more massive an object, the more matter it contains, the more gravitational pull it has. And so it turns out by measuring how fast this galaxy spins around, you can figure out how much matter, how much mass it contains. So this is a way for astronomers to weigh a galaxy and find out how big it is and how much material it contains. So Rubin wanted to do that, and so she pointed a telescope at various points in this galaxy, shown by these black dots here, measured how fast it was spinning, and this is what she found. So I'm going to show you a few graphs during this talk, but they're all fairly simple. This one, for example, shows the distance from the center of the galaxy. The center of the galaxy is here. This is to the left side, over here, and this part corresponds to the right side of the galaxy. And then this is just measuring how fast that galaxy spins around. Now, astronomers like to use kind of weird units, so we're measuring the speed in kilometers per second. So what does that mean? Well, just so you know, 100 kilometers per second is about 224,000 miles per hour, so it's pretty fast. If you were going that fast, you could get from here to New York City in about 30 seconds, which would be pretty convenient. So these galaxies spin fast. In fact, this one is spinning around at about 200 kilometers per second. And one side is spinning towards us, one side is spinning away. And it's spinning that fast even out a long way from the center. And that turns out to be a little strange, because if you count up all the stars in this galaxy and add up all of their mass, there's just not enough mass there to hold this galaxy together. It should fly apart. But it doesn't. So the idea was put forward that this galaxy must contain some unseen matter, some dark matter that's responsible for holding it together. So this was the first indication that we had dark matter in the universe. And we now have several other indications. A really beautiful example is something called gravitational lensing. So what you're looking at here is an image taken by the Hubble Space Telescope of a distant cluster of galaxies. So a cluster of galaxies is just when we have hundreds or a few thousand galaxies all kind of located together in one region of space. And in this image, each of these little yellow blobs is a single galaxy. Very beautiful looking. But if you look closely, and I don't know if we can just lower the light slightly, you'll notice some other strange features. For example, right here, this kind of stretched out line. There's another little line here, and another one down here. So what are those? Well, it turns out these are also galaxies whose light has been distorted by the effects of gravity. So when Einstein was putting together his theory of general relativity, which described how gravity works, he actually realized that light itself would be affected by the gravity of other objects. Now, light normally likes to travel in straight lines. The light from this projector leaves the projector and goes straight to the screen. But if I were to take a black hole and put it in the middle of the stage here, we'd all have a very bad evening, but if I did that, the light would no longer travel in a straight line. Instead, it would be curved. Its path would be curved as it passed by that black hole. And Einstein realized this could happen not only with black holes, but with any type of mass. And so what you're seeing in this image, here's us sitting on the Earth looking out into space. Here's our cluster of galaxies, which contains a lot of matter because it contains a lot of galaxies. And even further away in the universe, we have a distant galaxy. And the light traveling from that distant galaxy travels on a curved path because of the gravitational pull of this cluster. And it turns out, according to Einstein's theory, that the degree to which that light is curved depends on the amount of mass in this galaxy cluster. So I've been measuring the shape of these distorted images, what we call gravitational arcs. We can actually, once again, weigh this galaxy cluster. We can figure out how much mass it contains. And if we do that, we can then say, well, let's add up all of the mass in each of these galaxies and all of the other material that we can see in this galaxy cluster. And it turns out, once again, it's just not enough. It's not enough to explain how strongly gravitationally lensed these distant galaxies appear. So this galaxy cluster also seems to contain a lot of dark matter. So there are many other examples that we now know of, and we're very sure that the universe really does contain dark matter. So the question is, how much? So it turns out, kind of strangely perhaps, the best way to figure this out is to look at the Big Bang, the event that started our universe. So how do you look at the Big Bang? It happened 13.7 billion years ago. That's a long time. Well, fortunately, all of the light from the Big Bang is still around. So this was a very huge explosion, produced lots of light. In the intervening time, that light has kind of faded away as the universe has grown older and expanded, but it's still there, and if you look very closely, you can find it. And for the past sort of 10 to 15 years, we've had various experiments, including satellites, which have gone and tried to look for this light from the Big Bang. And so I'm going to show you a map of that. That's not a map of the Big Bang. This is a map of the Earth, as you can probably tell. Why am I showing you a map of the Earth? Well, the Earth is a sphere, right? It's a ball. And if I want to show you a map of the Earth, well, if I had a holographic projector, I could show you a 3D sphere. That would be great. But we don't live in Star Trek, so that's not possible. So if I want to show you a map of the Earth, what I have to do is take that sphere and kind of smush it down onto this flat screen so you can see it. And you're all used to looking at maps like this. Things get a little distorted, maybe at the North Pole here and at the South Pole, but you know what you're looking at. So the sky is also a sphere. We happen to be on the inside looking out, but that's okay. So if I want to show you a map of the sky, what I'm going to do is the same thing. I'm going to squash it down onto this flat screen. So okay, this really is now the light from the Big Bang, as measured by the Planck satellite very recently. And in fact, what you're looking at is not just the light from the Big Bang, but the variations in that light. So in some places in the universe, some places in the sky, that light is a little bit brighter, shown by the red colors here. And in some places, it's a little bit fainter, shown by the blue colors. And we can map that very accurately. These variations are very, very small, so you need a very sensitive experiment, but we can do that. So what has this got to do with dark matter? Well, it turns out this sort of splotchy pattern of bright and dark parts in the explosion and the Big Bang leftover radiation, that pattern we can actually predict, we can calculate what it should look like based on our understanding of dark matter. And it turns out that the pattern will change depending on how much dark matter the universe contains. And so by measuring this, we can then go back to our understanding of how dark matter works and figure out how much dark matter there is in the universe. And so we can actually figure out a cosmic composition. What is our universe made from? And the answer turns out to be a little strange, but here it is. So most of our universe turns out to be something called dark energy. Now, we're not going to talk about dark energy tonight. Maybe another year that would be a good subject, but tonight we're not going to mention it too much. Another good reason to not mention it too much is we don't know what it is. We have very little understanding, although there's a lot of work going on right now to try and figure it out. What we do know is that it makes up most of the energy in our universe, like I said, 73%, and it causes the expansion of our universe to get faster and faster with time. But if we set that aside for now and just look at the matter in the universe, the sort of stuff around us, it turns out 23% of that is dark matter. So if we ignore the dark energy, that's 85% of the contents of the universe, the matter of the universe, is dark matter. Less than 4% is hydrogen and helium gas, the two lightest elements in the periodic table. And most of that is just floating around in space, not doing a whole lot. There's then less than 1% of other stuff, and that other stuff includes about 0.5% of stars, so stars like our sun, smaller ones and bigger ones, stars of all kinds. 0.3% are things called neutrinos, which are just little subatomic particles. We'll come back to those later on. And then a tiny fraction, 0.03%, is what we astronomers call heavy elements, and that just means anything that's heavier than hydrogen and helium, so everything else in the periodic table, boron, carbon, nitrogen, oxygen, all of the stuff you're used to, all of the stuff that we're made from. So we're a very tiny fraction of the universe, which is great. It's nice to be special, so that's good. But what's really amazing about this, like I said, is that most of the universe is dark matter. Everything else is just a small blip on top of that. So scientists like to be very skeptical. We like to ask a lot of questions. It can get a little annoying, but it's good because that's how we figure things out. And so the first question you could ask is, well, maybe this dark matter is just normal matter. Maybe it's made from the same stuff we are, which is in the end protons and neutrons and electrons. Maybe it's just out there in space and it's just dark. It doesn't shine, so we can't see it. It could be just floating rocks. Well, it turns out that's not possible. And again, we can figure this out by looking back to the very start of the universe, back to the Big Bang. Now, shortly after the Big Bang, the universe was incredibly hot. This was a big explosion. Everything was incredibly hot. And in fact, in the first few minutes after the Big Bang, it had a temperature of 1 billion Kelvin. So Kelvin is just a measurement of temperature. For our purposes, you may as well think of it as being the same as a degree Fahrenheit, because if it's a billion Fahrenheit or a billion Kelvin, it's still really hot. And in fact, it's so hot that you can actually cook nuclei. You can cause nuclear fusion to happen. And that means I can take, for example, a hydrogen nucleus and a helium nucleus, and I slam them together and they stick and they form a new element. And in the first few minutes of the universe after the Big Bang, this process of nuclear fusion actually creates the first three elements in the periodic table: hydrogen, helium, and lithium. It doesn't really have time to make anything beyond that, but it makes these three. Now, it turns out we have a pretty good understanding of nuclear physics. It's complicated, but we understand it pretty well. And so we can actually calculate how many of each type of those elements will form after the Big Bang. So we can calculate how much of different isotopes or different types of hydrogen, how much helium, and how much lithium will form. And I'm just showing the relative numbers of each kind that are formed in the Big Bang here. And it turns out that the relative number of each of those elements that is created depends on the amount of normal matter, protons and neutrons, that exist in the universe. And so what I've done is done this calculation of how many of each element should form, and I've changed the amount of normal matter in the universe. And I've written this down as just as a fraction of the total amount of matter that would be needed to explain all of dark matter. So if normal matter explained all of dark matter, I'd be right here. I'd expect to have this much lithium, this much hydrogen, and so on. And now we can actually go out and measure this in the universe. We can go and look at how much of each type of these elements is actually found out there. And the observations lie along this line. And if we read off, that tells us that only about just over 10% of the total amount of dark matter could be explained by the normal things we know of, protons and neutrons. So whatever dark matter is, it's not normal matter. It's not anything we're used to. It has to be something new and unexplained as yet. So that's pretty exciting. So if you continue being skeptical, we can also ask, well, are we really sure there's dark matter out there? You know, do we trust all of our calculations? Well, really what we're doing here is trusting our understanding of how gravity works. When we weighed that galaxy, that rotating galaxy, by looking at how fast it spins around, we were using our understanding of gravity to figure out how much mass it contained. When we looked at that lensing cluster of galaxies, we used our understanding of gravity to figure out how much the light should be bent by the mass in that galaxy cluster. So we're trusting our laws of gravity, but it turns out this trust has actually paid off before in many cases. So here's a good example. So back in the 19th century, astronomers were still trying to figure out what was in our own solar system, how many planets there were, what else was out there. And so this guy, Urbain Le Verrier, was very interested in that, and he was particularly interested in the planet Uranus. And he said, well, Newton's told us how gravity works, so I should be able to figure out how the planet Uranus should move around the sun. So he did the math, figured it out, looked at where the planet Uranus was, and calculated, well, tomorrow it should be at this point in the sky, the day after it should be over here. And it turns out he was wrong. It didn't work. It was pretty close, but it wasn't perfectly right. And so he said, well, I actually think our laws of gravity are correct. They've worked in every other case. We've tried them extremely well. So I have no reason to believe they shouldn't still be working in this case. And he said, well, the only other possibility then is that I left something out of my calculations. Maybe there's another planet out there that nobody has seen yet that's sort of pulling on Uranus and causing it to move in a way slightly different than what I expected. And so he did some more math. I guess he liked math. And he figured out, where would I have to put a planet in order to cause Uranus to move in the way that I actually observe it to move? So he did those calculations. He called up his friend Johann Galle. Well, maybe he sent him a letter, I guess, but somehow he told him, this is where I think there's a new planet that nobody has seen. And Galle took his telescope, pointed in that direction, and within an hour found Neptune, a planet that nobody knew about. It was pretty spectacular. And this is all based on trusting our understanding of how gravity works. So we really think there is dark matter out there. So I wanted to take a couple of minutes and just show you some visualizations of dark matter, what what we think the distribution of dark matter in the universe looks like, and explain to you how we can actually do that. But before I do so, I just wanted to take a minute here and show you an image of galaxies, since that's actually what I spend a lot of my time thinking about. I think they look cool, so I'll show you some. This is an image of a patch of the sky filled with galaxies, kind of thing that the Hubble Space Telescope would see. So each one of these little blobs is an individual galaxy, except that this isn't actually the real sky. This is the sky in a model universe. So what we did was to take our understanding of how dark matter and galaxies work, feed all of that into our big computer at Carnegie, and run a calculation and figure out what would that universe, that model universe, look like if I could put the Hubble Space Telescope in the computer and make it look through it. And this is the answer. So it's filled with galaxies, thousands and thousands of them. And yeah, I'm pretty proud of this. I think it's cool, so I'm going to show you it. But it also serves a purpose. So one of the nice things about being a theoretical astrophysicist is that once we've built these models, we can go and start changing things. We can change the rules. And so in particular, in this case, I can say, well, what would happen if I just take all of the dark matter out of this calculation? So I'll show you. This is what happens when I take all of the dark matter out of that model. There's nothing left. So why is that? Well, dark matter is most of the matter of the universe. It's 85%. So it provides most of the gravitational pull. And these galaxies that we were looking at are actually very dense systems. There's been a lot of matter concentrated into one region to form this galaxy. So if I take away the dark matter and take away its gravity, there's nothing left to pull that matter together. And so as a result, no galaxies form. So the mere fact that we see galaxies in our universe is yet another indication that we have to have a lot of dark matter. So let's put it back because it looks nicer. So I want to show you a couple of movies of the distribution of dark matter in our universe. So these are computer calculations, and in principle they're very simple. As you'll see in a minute, we think dark matter is some kind of particle, and so we just feed into our computers a representation of dark matter. We tell it, put all of these particles of dark matter. This is how we think they're spread around in the very earliest stages of the universe. And then we tell the computer to calculate the forces of gravity between each of those particles. And once it's calculated the forces of gravity, it knows how those particles now have to move around. And it can keep doing that for 13.7 billion years, although it does it much faster, until we get to the present day, and we can look at how that dark matter has turned out to be distributed around us. And of course, once again, since this is a model universe, we can change the rules slightly. We can say, let's light up this dark matter. Dark matter is normally dark, we can't see it. But we can change the rules and say, let's make each particle of dark matter bright so we can look at it and visualize how it's distributed. And so I'm going to show you the first movie here. If I can. Okay, so I'm just going to pause it very quickly. It doesn't look very impressive, huh? What you're looking at here is the distribution of dark matter shortly after the universe began. And it looks more or less the same everywhere. The universe, when it began, was very smooth. And so you can maybe just make out there are some parts that are slightly brighter, some parts that are slightly darker. And because I've made the dark matter light up, where the screen looks brighter, there's more dark matter gathered together. So let's just let this run on for a few seconds here. You'll see things start to change. And this is because of the effects of gravity. So gravity likes to pull things together. So you can see, for example, in this region, gravity has started to pull together particles of dark matter and concentrate them into a region. And this little blob of dark matter is something we call a dark matter halo. And we call it that because we think that's where galaxies form. A galaxy will form in the center of that blob of dark matter, and so the dark matter will be sort of like a halo surrounding the galaxy. I'm going to let it run on just a slightly further. And you can probably begin to see now that connecting these dark matter halos, like this one and this one, there are filaments of material. This is also dark matter. And this is sort of a characteristic feature we find whenever we do these calculations. The dark matter halo is formed, and they're connected by this filamentary, what we call cosmic web of material. And I'm just going to let this run on, and what you'll see is that this process just keeps happening. We form bigger and bigger dark matter halos as gravity pulls more and more matter together. So we're forming a very big one here. But you'll notice there are still lots of smaller dark matter halos lying around nearby. And this keeps on going. We're going to have a nice big merger between two dark matter halos here, 3 of them actually. They'll merge together and form bigger and bigger systems. So that's how we can visualize how dark matter is arranged in the universe. And that was a pretty big patch of the universe. What I'm going to do now is just zoom in to a pair of dark matter halos. And we're just going to rotate around them so we can see in a little more detail how they're structured. So here we go. We're rotating around this pair of big dark matter halos, but you'll notice there's a lot of smaller ones lurking around nearby as well. And this is actually what we think the dark matter around our own Milky Way galaxy looks like. Here would be the Milky Way, and here would be the Andromeda galaxy, our nearest neighbor. And these are really cool. I mean, I think these are just really beautiful, stunning representations of what we can calculate about how dark matter is spread around the nearby regions of our universe. Cool. Well, that doesn't help. There we go. Still going. So I'm just going to leave that there for a second so you can take it all in. And like I said, these calculations we now have got very good at doing them. We can do these calculations in great detail, and they're a really useful tool for us to understand the properties of dark matter and where it might be located in the universe. Okay. So I've been talking about dark matter, but I haven't told you what it is. There's a really good reason for that. Nobody knows. We don't know what dark matter is. But we have some ideas. And in fact, when astronomers discovered that the universe contains dark matter, one of the first things we did was to go to talk to our particle physics colleagues and ask them if they had any leftover particles that they weren't using for anything that might make a good candidate for dark matter. Now, particle physicists have lots of great ideas. They're never short of that. So they, in fact, came up with a whole list of possibilities. And for some reason, particle physicists always like really weird names as well. So these things all have kind of silly names. But let me explain to you just briefly what some of them are. So the most plausible type of dark matter is something we call WIMPs. It stands for weakly interacting massive particle, which really just describes what it is. So it would be a massive particle, something like 100 times heavier than, say, a hydrogen atom. This is pretty big as particles go. And it would have to interact with other matter very weakly. And we know that's the case because if it interacted with normal matter, like the things in this room, if it interacted with them strongly, well, we would have already noticed it. So it has to be just very weakly interacting. And it turns out these WIMPs are a natural consequence of something particle physicists call supersymmetry theory. Now, we're not going to get into what that is. The point is that they already had a problem in their own branch of physics that they were trying to solve. And they solved it with something called supersymmetry theory, and it naturally predicted these WIMP particles. And that's quite nice. That makes things kind of neat. If these particles can solve a problem in particle physics and also explain why we have dark matter in the universe, that would solve 2 big problems in one go, and that's nice. So they had a whole bunch of other ideas as well. Dark matter could also be a type of particle called an axion. So these are just light, neutral particles that fly around. Dark matter basically has to be electrically neutral. It cannot have a charge, like a proton or an electron would, because if it had a charge, it would be able to interact with light. And if it could interact with light, we'd be able to see it. So we know it pretty much has to be neutral. And once again, these axions were introduced by particle physicists to solve a problem that they had. In this case, something called the CP symmetry problem, which again, we're not going to worry about the details, but once again, it's just nice that you can solve multiple problems at one time. And then we get into the crazy stuff, the exotica, which has the really wacky names. So we have things like WIMPzillas and Q-balls and gravitinos. There's a whole menagerie of possible particles that could be dark matter. And so one of our jobs as scientists is to try to figure out which of these might actually be correct. And so there's a lot of work going on trying to actually detect these particles. So we think of dark matter as being out there in the universe, but in fact it's also right here in this room. So dark matter particles are flying through this room right now, flying through your bodies. Don't worry about it, it's not going to hurt. It's been happening all the time. Because dark matter only interacts very weakly with normal matter, particles of dark matter can pass right through the Earth without even noticing it. But because there's dark matter in this room, that means maybe we could actually detect it if we built a very sensitive dark matter detector. And so a lot of people are trying to do that. Here's one example. So this is an experiment called Super CDMS. The CDMS stands for Cryogenic Dark Matter Search. And this is an experiment being run out of Stanford. And basically what they're doing is building a lot of detectors like this. So this is just a piece of semiconductor. So kind of like the stuff that we make microchips in computers out of. And the idea is that this piece of semiconductor will be sitting around and occasionally a dark matter particle might pass through it. And just very, very occasionally, that dark matter particle might collide with a nucleus in this semiconductor. Won't happen very often, but we think maybe just occasionally it will. And this detector can actually see that happening. It notices it because it causes ionization, so it causes electrons to be ejected out of this atom. And it also causes this detector to vibrate at a very low level, but nevertheless, if you're careful, you can detect that. Now, as we said, dark matter only interacts very weakly, so one of the problems with these kind of experiments is that there's a whole lot of other stuff out there that can also collide with your detector, and you need to figure out which ones were dark matter and which ones were just other boring stuff that we don't care about. And so one of the things that happens is that we take these detectors and we put them deep underground. These ones are actually going to be based at the bottom of a mine shaft in northern Minnesota. And we do that because then you get to use the entire Earth, the surface of the Earth above you, as a shield. It blocks out all of the other sources of particles which might collide with your detector. Only the dark matter can get that deep underground and interact with the experiment. So there's a lot of experiments like this going on around the world, and this really would be the sort of ultimate in dark matter detection if we can actually detect the particle. And so there are a lot of people doing it. If you find dark matter, you're pretty much guaranteed to get a Nobel Prize, I think. So there's a big goal here, and also just finding 85% of the universe. But as yet, none of them have been successful. There have been some tantalizing hints, but there's nothing definitive that says we've detected dark matter. So what do we do? Well, so far, astronomy is the only way that we know anything about dark matter at all. That's how dark matter was detected, and as you'll see in a minute, is how we've learned a few interesting little pieces of knowledge about what dark matter might be. So if astronomy is the only way we know anything about dark matter, maybe we should just continue trying to use astronomy to learn more about the nature of dark matter. There's another really good reason to do this. If you want to do a direct detection experiment and find dark matter, you spend most of your time at the bottom of a mine shaft. If you want to do astronomy, you might get to go to a beautiful mountaintop in Chile, or you go to Hawaii. You choose. So we can ask, what else can we figure out about dark matter using astronomy? Well, we can't really detect the individual particles that are out there in the universe, far too far away for us to actually detect individual particles, but maybe we can learn something about their phenomenology. Well, this is a fancy word. All it really means is that we can learn something about their properties and how the dark matter behaves. So really, this is basically just a game of cosmological 20 questions. We're going to ask a bunch of questions and try to answer them. And in doing so, we can figure out what dark matter is. The advantage here is that there's no limit. We can ask as many questions as we like. So we can just keep coming up with more and more ways that we can learn about dark matter. So what kind of questions can we ask? Well, we can ask things like, is the dark matter particle more massive than 2 keV? So here's one of these other crazy units that we like to use. keV here is just a measure of how massive that particle is. So to give you an idea of what that means, if you went down to the grocery store and bought yourself a 1-pound bag of dark matter, it would contain something like 100,000 billion particles of dark matter. So it's tiny. It's a very, very small mass. And we can also ask questions like, does this dark matter particle interact in any way with normal matter? Can we understand to what degree that is or is not true? And kind of just like in the game 20 questions, what we're trying to do here is rule out possibilities. If we ask, when we're playing 20 questions, is it bigger than a bread box? If the answer is yes, then we know it's not an apple. We know it's not a mouse, right? You can rule out a whole categories of possibilities, and that really narrows down the options that are left. And maybe if we narrow down the options enough, we can go and tell our particle physics colleagues, here's where you should be looking to find dark matter. So one of the first questions that anybody asked about dark matter in this way, and this happened about 30 years ago now, was to ask, is dark matter hot or cold? So what does that mean? Well, on a hot day in Southern California, like last week, it feels hot because the molecules in the air are moving around very fast. And when they collide with our body, we feel that as a high temperature. So, sort of similarly, hot dark matter would be dark matter that moves around extremely fast. And in fact, it would move around at the speed of light, or very close to it. So a good example of that is if dark matter was made from neutrinos. That would be kind of nice because those are particles we know actually exist. The alternative is that dark matter could be cold. The particles are only moving around very, very slowly. And examples of that would be axions or neutralinos, which are a kind of WIMP, one of those weakly interacting massive particles. And so back in the early 1980s, when people were first starting to do these computer calculations of how dark matter should be distributed in the universe, one of the first things they did was to say, let's build one model using cold dark matter and one model using hot dark matter and see if they look different. So here's the answers. This is actually a more modern simulation, but the ideas haven't changed since 30 years ago. So on the top here, we have cold dark matter. And we're looking at, once again, a sort of fairly large region of the universe on the left here. And then we're zooming in to a smaller single dark matter halo on the right. And on the bottom, we have the exact same model universe, but now calculated using hot dark matter. And in the middle, we have something kind of in between, so sort of warmish dark matter, which we'll get back to in a few minutes. So you can see they look very different. The hot dark matter looks much smoother. If you look at this cold dark matter case, you see all sorts of tiny, detailed filamentary structure, lots of little tiny dark matter halos lurking around here. Down here, not so much. So why is that? Well, all of this structure is created by gravity pulling dark matter together. In the case of hot dark matter, it really is kind of like herding cats, right? So if you have a bunch of cats and you want to get them into a box. So you pick up your first cat, you put it in the box, you go and find the second one. By the time you got back, the first cat's already run away. It's already bored of that, it's gone. And so gravity is trying to pull these hot dark matter particles together to form a dark matter halo, but every time it does that, some of them just stream right out, they leave. So it makes it very difficult for gravity to form structures in hot dark matter. Cold dark matter, on the other hand, is kind of like herding sloths. And you pick up your sloth, you put it in the box, you go and get another sloth, you bring that back, and the first one is still just sitting there. It's not going anywhere. So it's really easy to bring them all together into one place. And that's what happens in the cold dark matter case. Gravity is able to efficiently pull all of this dark matter together and form this wonderful detailed cosmic web. And once we've done these calculations, we can go and look at what the actual universe looks like. So we can go out and survey the universe and find where all of the galaxies are located. And because we know dark matter makes up 85% of the mass of the universe, it has most of the gravity. So wherever the dark matter goes, the galaxies have to go along with it. So by looking at the pattern of galaxies on the sky, we can compare it to these two calculations. And it turns out it looks by far most like this cold dark matter case. So even as early as 30 years ago, we could rule out hot dark matter. We knew dark matter was not made of neutrinos. So that's by asking one of these kind of phenomenology questions, which allows us to understand the properties of dark matter and how it behaves and rule out certain possibilities. So let's do a couple of other questions like that. So we can ask, does dark matter annihilate? So every particle in our universe has an antiparticle. We have protons, we have antiprotons. And if those particles collide with each other, they annihilate in a burst of gamma rays, just very high energy light. So it turns out that dark matter perhaps could be its own antiparticle, which sounds a little weird, but that actually happens for other particles. So dark matter could be two. And that would mean every time two dark matter particles happen to run into each other, they would annihilate and there'd be a whole burst of gamma rays coming out. Well, it turns out that would be very convenient because we have right now a satellite orbiting the Earth called Fermi, which can see gamma rays. So if we think we know where dark matter annihilation would be happening, we can make the Fermi telescope look there and see if we see any gamma rays that might be coming from dark matter. And so this is an example of what we think the sky would look like if we could see gamma rays from dark matter annihilation. So again, this is a map of the whole sky, once again squashed down onto the page here. And this is one of these model universe calculations. So a group of theorists did a computer calculation of where they think the dark matter should be located around our own Milky Way. And then they said, well, let's assume that that dark matter undergoes annihilation. Where would we see most of the gamma rays? And you can see very clearly that most of the gamma rays would be coming from right here. And they've arranged this map such that the middle of it is the center of our own galaxy, the center of the Milky Way. And that kind of makes sense. I mean, most of the stars in the Milky Way are concentrated towards the center. We might expect that's where most of the dark matter lies as well. And when we have most of the dark matter, it's much more likely then that two particles will run into each other and annihilate. So we expect to get more gamma rays coming from where most of the dark matter lies. And you'll notice there are a couple of other bright points around. These correspond to some of those smaller dark matter halos that we've seen in some of the movies. We see them lurking around. So they're quite bright as well. But by far, most of the gamma rays would be coming from the galactic center. So great. Let's go and point the Fermi telescope at the middle of our galaxy and see what it sees. So this was recently done, and this is some work that appeared just this year by Dalen. And what they did was to look at the center of the galaxy using the Fermi satellite. We're seeing this is both the center of the galaxy in each of these panels here. We're just looking at slightly different energies of gamma ray light. But it shows more or less the same thing. And great, we actually see gamma rays coming from the galactic center. We have to be a little cautious here. Dark matter is not the only thing that can make gamma rays. Turns out the center of our galaxy is full of all sorts of weird things, like black holes and pulsars, some of which might be able to emit gamma rays of their own. So what Dalen had to do was to try to figure out how many gamma rays were coming from those other objects, say from pulsars, and then kind of subtract away all of those uninteresting gamma rays and see if there was anything left. So when they did that, this is what they found. And it turns out there is a little bit of gamma ray light that cannot be explained by any of the known pulsars, black holes, or anything else at the center of our galaxy. So if this is correct, and if this is really light coming from dark matter, this would be really exciting. It would tell us, for example, that the dark matter particle has a mass of something like 40 times that of a proton. And it would also tell us that it's its own antiparticle since it's annihilating. That would be really useful knowledge about dark matter. So this is really exciting. We have to be a little cautious again, though. Any result that's sort of this big, we have to check and recheck and really be sure that we've done everything right. So in this case, you could imagine, well, what if we haven't completely removed all of the gamma rays coming from those other things, those pulsars? What if there are actually more of them than we thought? Then if we subtracted away that extra light, maybe there'd be nothing left. So although this is really exciting, we cannot claim yet that we've actually detected a signal of dark matter. But we're getting close. We're getting to the point where we're starting to get some very interesting, very tantalizing evidence. And hopefully in a year or two, we'll actually know if this is really dark matter. So I want to show you sort of one last topic, one last idea of how we can learn about the nature of dark matter. And we're going to do that using the very smallest galaxies in the universe. So this is a map of our own local group of galaxies, our own region of space. So right here in the center is the Milky Way galaxy, where we live. Over here is the Andromeda galaxy, which is about the same size as the Milky Way. And then there's a whole bunch of smaller, what we call dwarf galaxies, lurking around, sort of orbiting around the Milky Way, some of them orbiting around Andromeda, others just kind of scattered through space. And this, once again, is a map of dark matter. Again, one of these computer calculations of where dark matter should be located. And just so you know, this whole region here corresponds to this much larger region on the right. So this is a sort of a zoom in of this little region. And so we have galaxies, we have dark matter, and what we want to do is compare the two. So how can we do that? Well, I'm going to use a very advanced mathematical technique to do this, and don't worry, I'll sort of show you how it works. It kind of works like this. 1, 2, 3. We're just going to count them. It's the most simple thing you could possibly imagine doing. We're just going to count up how many galaxies we see, and we're going to count up how many dark matter halos we see. So just so you don't think this is too easy, the counting part is trivial, but actually the difficult part is, first of all, doing these calculations of where dark matter is distributed and finding these galaxies. So just to convince you how difficult that is, here is one of those dwarf galaxies. It's called Willman 1. And I don't know if you can see it, but I'm not sure I can. Each one of these little green circles circles a single star in that galaxy. But really, there's not much to see there. The reason it's difficult to see anything is that the Milky Way, our own galaxy, is getting in the way. We have to look through all of the stars in the Milky Way just to see this dwarf galaxy. And so to bring it out, what Willman did was to, again, subtract away all of the uninteresting stuff, to remove all of those stars in the Milky Way and see what was left at the end. And here's the result of that. When you subtract away the Milky Way, what you're left with is this little galaxy lurking there, just hidden amongst this whole mess of stars from our own Milky Way. So that's the difficult part. But once we've done that, it's really easy to count up galaxies. Now before we can compare these two, there are two things we have to sort of take into account. The first is that maybe we haven't found all of the dwarf galaxies that are actually out there. We know of something like 20 or 30 or so just around the Milky Way, but we haven't looked for them in all of the sky. We've only looked in one patch of the sky. And so it's quite possible that there's more of them over here, more of them over here. So we really need to account for those ones that we haven't yet discovered. And we can do that. We can do some careful calculations and figure out where we think those other galaxies might be. And once we do that, it turns out that maybe there are something between 100 and 200 dwarf galaxies waiting to be found. So 100 to 200 galaxies. Now we think each of those galaxies formed inside a dark matter halo. So if we look on the left here, well, I'm not going to try and count these, but you can see that there are thousands of dark matter halos in this model of dark matter. So that's okay. I can think of several ways in which some of these dark matter halos maybe never formed a galaxy. Maybe they were just so small that gravitational pull wasn't enough to concentrate matter and form a galaxy. So some of them may just have no galaxy in them. That's okay. But what if I had the reverse problem? What if I had so few of these dark matter halos that just weren't enough to make the galaxies that we see? That would be a problem that we wouldn't really be able to explain. And so any type of dark matter that produced so few dark matter halos, less than about 100 or so, we could actually rule that out. We could say that model of dark matter cannot possibly be valid because it couldn't form enough galaxies around the Milky Way. So we can actually use that to determine if dark matter is not hot, but maybe it's just warm. Maybe it's not perfectly cold. Maybe the particles are moving around, not quite at the speed of light, but still pretty fast. So once again, I'm going to show you some model calculations here. This is work that was done by Mark Lovell just last year. So what you're looking at once again is a calculation of how dark matter is spread around our own Milky Way. And this is again assuming that dark matter is completely cold. It's a cold particle, not moving around very fast at all. And we can see that we form thousands of these dark matter halos. So let's dial up the temperature a little bit. Let's make this dark matter warm. Not so hot that we already know it can't work, but we'll make it warm. So here's warm dark matter where the particle has a mass of 2.3 keV. And you can already see that it looks slightly different. It's smoother. And this is once again because these particles are now moving around a little bit faster. They can escape the pull of gravity, and so we don't form quite as much detail. So let's make the dark matter warmer still. If we lower the mass of the particles, they will move faster again and be a little warmer. So things get a little bit smoother. If I lower the mass again, smoother still, once more, and we have a very smooth distribution of dark matter. And you can see that there are now only a few of these dark matter halos surviving. Most of the rest we've sort of washed away by heating up the dark matter. And so we can go into each of these cases and just count up how many halos we find, and we better have at least 100 or so in order to explain the number of dwarf galaxies that we see around the Milky Way. So here's the result. This looks a little bit complicated, but really all I'm doing is counting how many dark matter halos I find in that calculation. And I'm counting how many big ones and how many small ones, but we don't really care about that too much. All we care about is the total number of dark matter halos that we find. So if we have cold dark matter, we find something like 30,000 dark matter halos. 30,000 is much bigger than 100. That's great. We have enough halos to make all of the observed galaxies. But what if I go to warm dark matter and have a particle with a mass of 2.3 keV? I get this blue line. It only produces about 120, 130 dark matter halos. That's just about the right number to explain all of the dwarf galaxies that we observe. If I make it too warm, like this red line, where I have a particle with a mass of just 1.5 keV, then I'm left with something like 30 dark matter halos. And that's just too few. There's now no way that I can make enough dark matter halos for all of the observed galaxies to form it. So this is really great. Just by counting up dark matter halos and counting up galaxies and comparing the two, we've been able to figure out that the dark matter particle must have a mass of at least 2.3 keV. Any possible particles which have a mass less than that, we now know are not going to be dark matter. And that's the kind of information we can then pass on to our particle physics colleagues and say, don't bother looking for these guys, it just won't work. And we can take this same idea and apply it to all sorts of other possible questions about dark matter. So one that we asked recently was, does dark matter decay? So if you take any kind of particle, leave it just hanging around, most of them will sit there for a while and then sort of spontaneously break apart into other particles. And maybe dark matter does that as well. We don't know. So let's figure out what would happen if it did. And so the idea is very simple. We have some particle of dark matter. We'll call it X because we don't know what it is. And it sits around for a long time, and then it splits apart into two other particles. We'll call one Y, and we'll call one squiggly Greek letter. And so with my colleague Annika Peter, we actually calculated what would happen if dark matter underwent this kind of decay. Now when a particle splits apart, one particle moves off in this direction, one moves off in this direction, moving with some speed. And that has basically heated up the dark matter again. We're making the dark matter move around faster than it was before. That means it's warmer than it was before. And so we once again expect it to become difficult for gravity to hold the dark matter in place. And so once again, we'd smooth out all of those small dark matter halos that formed. And if we smooth it out too much, we won't have enough dark matter halos to form all of those observed galaxies. So we did the calculations here, and we actually did it for a whole bunch of different types of decaying dark matter. So we changed how long it takes for the dark matter particle to decay, how long it sits around before it splits in two. And we changed how fast those particles move after they decay. And then we just ran our calculations, counted up how many dark matter halos formed, and asked if it was enough. And it turns out in this blue and pink region, if decaying dark matter has properties that lie in this region, there's just no way it can form enough dark matter halos. So we can rule out this entire set of possibilities. The green region is still okay. If when dark matter decays, the particles only move off with very, very low speeds, that's okay because we haven't heated the dark matter up very much. It's still basically cold, so we still form a lot of dark matter halos. And also, if we make it sit around for a very long time, 1,000 billion years before it decays, well, then we don't have a problem either. The universe is only 13.7 billion years old, so most of the dark matter is still hasn't decayed. It really hasn't done anything yet. But we can rule out this whole big region. And once again, that's very powerful because now any possible particle that we think might be dark matter, we can check if it has properties in this range. We can already say that's no good, it's not going to work. So it allows us to limit the possibilities. So the final thing I wanted to show you was just some very new results which I think are really exciting. And this is once again using gravitational lensing. So we talked about this earlier, this idea that comes out of Einstein's theory of gravity, that light from a distant object will travel along a curved path as it passes by some massive collection of matter. And here's a really nice example of that happening. This is work by Simona Vegetti that was from a couple of years ago now. And they looked at one of these gravitational lenses, one of these arcs, where the image of a galaxy has been strongly distorted and stretched out by this process of gravitational lensing. And in this case, the lensing was so strong that it actually made almost a perfect circle. It made this galaxy's image appear to be bent into a perfect circle. This is something we call an Einstein ring. It's not quite perfect, but it's pretty close. These are really, really stunning images, I think. It's really amazing that this can happen in the universe. And so what Vegetti did was to say, well, let's try and understand the details of this gravitational lens. And so they built a model of what they thought it should look like based on the mass that they could see out there in front of this galaxy. And here's that model. And if you compare the two, you can see they're pretty close. So that model works quite well. So that means they have a good understanding of where the mass is located around this gravitational lens. But they said, well, okay, let's look very carefully though. And what they did was to sort of look at the difference between what they actually see and what their model says they should see. And that's shown over here, and it kind of looks like a sort of speckled donut shape. But it turns out there is actually something left in there. There is something left in the difference. The model does not completely match the data. And it's very, very small, so it's very difficult to see. But what they did was to do some more careful analysis here, and they could figure out that there must be some extra mass associated with this gravitational lens. And it turns out that extra mass is right here. Now we don't see any light coming from that region. No light at all, but there is mass there. So this seems to be dark matter. Seems to be a dark matter halo, a fairly low mass one, that they've detected just because it slightly changes the distribution of light in this gravitational lens. So this is really powerful. This means we have a way of detecting dark matter halos out there in the universe that don't contain a galaxy, don't contain any light. We can detect them purely because they cause gravitational lensing. Now, so far they only have really one example of this, but they're hard at work trying to find more examples. And if we do that, we can begin to build up a picture of dark matter halos. We can count up how many there are, what masses they have, where they're located relative to the galaxy that's causing the lensing to happen, so we can begin to study their properties. And so the thing I wanted to end on here was sort of where this is going in the future. And so because of these results, I've been working with some of my colleagues at JPL who are interested in putting up a satellite which will try to look for more of these lensing systems. And we'll try to find many of them and do this measurement, count up how many dark matter halos there are and what their masses are. And so working with Anthony Pullen, who's a scientist at JPL, we've been making calculations of where we think dark matter halos are located around these gravitational lenses. So this is just a schematic picture. Each of these blue circles is a single dark matter halo that we might be able to detect using this gravitational lensing method. And the bigger they are, the more massive they are, and we can see they're spread around in space around the center of the lens, which would be right here. So this is just one example of where dark matter halos might be located around one gravitational lens. So what we're doing now is repeating this many times, thousands or maybe tens of thousands of times, to build up a whole catalog of all of the possible arrangements of dark matter halos around every type of lens we can think of. And we're doing that for cold dark matter, but once we've done that, we're going to repeat this and do it for warm dark matter, for self-interacting dark matter, for decaying dark matter, for every kind of dark matter we can think of. And once we've done that, we'll have this beautiful data set that tells us what this Omega satellite should see if and when it gets out there into the universe and starts looking for these lenses. And then by comparing the results from this satellite with this data set that we've built up, we should be able to figure out what type of dark matter is out there. Is it cold? Is it warm? What else does it do? And I think if we can do that successfully, we'll then have a pretty good understanding of the properties of dark matter. We maybe won't know what kind of particle it is, but knowing the properties, we can go once again back to our particle physics colleagues and tell them this is the kind of experiment you need to build in order to detect dark matter here on Earth. And I think if that is successful, that really is going to be one of the biggest scientific achievements of the 21st century. Finding 85% of the universe would be absolutely spectacular. Thank you. And if we have any questions, I'm happy to answer. Do you want to go ahead?
Well, if you look at it as an iceberg, with the matter up here, and then, your grand unified theories and your string theories is dealing with this little bit of the iceberg up here. What about, aren't you guys messing around with the dark matter and dark energy going to kind of screw there? You're going to show up with it?
That's a very good question. Yeah, so most of... Oh, sure. So the question was that so people who are working on grand unified theories of physics or string theories are really focusing on this just 4% of matter, the normal matter that we see around us. And so the question was, should they be worried because we have all of this dark matter and dark energy that they're maybe not accounting for? Well, the answer is that they're well aware of dark matter and dark energy, and they would be very, very happy if their theories actually predicted it. So they know about this, and it's certainly something that they take into consideration. And you can see that they have several ideas of what it might be, but as yet there's nothing conclusive. There's no particle that we know of that has actually been detected that could explain dark matter. Yep.
How does dark matter compare to the ancient theory of the heavenly ether, which was supposed to permeate the universe and aid the propagation of light?
Right, so the question was, how does dark matter compare with the old theory of ether, which was supposed to be a substance which sort of permeated the universe and which light traveled through? So dark matter is actually very different. It's in many ways just like any other kind of matter. It's a particle. We don't know what it is, so in that sense it's very, it's unknown, but it's not like the ether in that it's not like other particles move through it. It's just a particle in its own right. So I think they're really separate concepts.
Do we only know it exists because of its gravitational effect? Is that the only indication? So does that mean then that it even has to be in this universe at all? It could just be the effect of, we're on a fabric and then there's another magnet behind the fabric.
So this is a really good question. So the question was, do we only know of dark matter because of its gravitational effects? And if that is the case, could it be that dark matter is not even in our universe? To answer the first part, yes, it's only through its gravitational effects that we know about dark matter at all. We have not detected it interacting with matter in any other kind of way. So it's purely through gravity. And in fact, people have proposed theories in which there's essentially a second universe parallel to our own, which has its own mass, has its own stuff in it, and we can feel the gravitational pull of that stuff, and that is what dark matter is. So I think those theories are pretty speculative, and they're certainly not the most popular theories for what dark matter could be. But on the other hand, it's certainly not impossible. It would be kind of depressing if that was the case, because it would mean that we have no hope of actually detecting dark matter in the lab. The only way we would ever know about it is through gravity. So I guess that's good for astronomers, but bad for particle physicists. Yeah.
You've talked about attempts to measure, detect dark matter on galactic length scales and also in laboratory length scales. And between those, there's a tremendous, very big range. There's stellar length scales, solar system, things like that. Have there any attempts to do any sort of experimentation or observations on those sort of things?
Yeah, so that turns out to be very difficult. The problem is that it's, repeat the question. So the question was, we've identified dark matter on very large scales, on the sizes of galaxies or bigger, and we're also looking for dark matter in the lab, so on very small scales. Can we detect it? Can we try to find it on scales intermediate to that? So that's very difficult. The reason is that, for example, in our own solar system, so out between the planets, dark matter is a very small fraction of what's out there. Because normal matter likes to clump into stars and planets and galaxies, all around us, in the Milky Way, for example, most of the matter is normal matter. There's only a relatively small fraction of dark matter. It's only when you get out into very big scales in the universe that dark matter becomes the sort of major component of what's out there. So that means it's very difficult to detect anywhere nearby. We'd have to be able to very, very accurately remove the gravity of all of the other matter before we could detect dark matter, and that's very difficult. So we tend to look just on scales of galaxies, galaxy clusters, or the scale of the whole universe. Yeah. Yeah, go ahead, please.
Since you're hypothesizing that it's maybe a particle, could it be that it has its own chemistry and that there's a whole new type of reality? Or maybe that's connected to these other questions that you've answered obliquely in a way.
No, that's a great question. So the question was, could dark matter essentially have its own chemistry? So one of the great things about it is because we don't know what it is, you're free to speculate almost anything you like. And believe me, people have done that. So people have actually proposed the idea that we have dark matter chemistry. There are the dark matter equivalents of protons and electrons, and they would form dark matter hydrogen atoms. The problem with these ideas is that they're usually incredibly difficult to test. How would we know if that was the case? We really need some kind of signature, some kind of signal from that dark matter chemistry that we can see in order to be able to say, yes, that's the right theory. In the absence of that, we tend to prefer to have just the simplest kind of dark matter we can think of. So it would just be a single particle, no chemistry. But those possibilities are totally open. We just don't know right now. Yeah, please go ahead.
A few years ago, there was some talk about something called a dark flow, and it looked like dark matter was moving towards the edge of the universe. Have you heard anything new about that? Is it panned out, or is that just gone away?
Yeah, so the question is that a few years ago, there was some evidence that dark matter was flowing into a particular direction in the universe. And is that still the case, or has that gone away? So suddenly, nearby, in cosmic terms, so nearby to our own galaxy, dark matter is moving towards some of the nearest clusters of galaxies. Their gravity is pulling us, our own Milky Way, and all of the dark matter with it, pulling us towards it. So on those small scales, there is a flow of dark matter. But if you go to the scale of the universe as a whole, then the dark matter is not flowing in any particular direction, as far as we're aware. Instead, it's all just moving apart from each other as the universe expands in a fairly uniform way. Sure. One way in the back there? Yep.
Who coined the phrase dark matter? And before it became the consensus, were there any other terms that were bandied about?
So the question was who coined the phrase dark matter and were there any other competing terms? So as far as I'm aware, and I think this is not just an anecdote, I think this is true, that it was first called that by Fritz Vicky, who was an astronomer at Caltech, and I believe he called it Dunkelmatter, or whatever the equivalent German is. I don't speak German. But literally meant stuff that's dark, stuff that he couldn't see. And as far as I'm aware, I don't think there have been any competing terms. I think that's always sort of been the term that has been adopted. So, one over there?
There have been a lot of efforts to have an enhanced gravity theory to handle the accelerated expansion of the universe and inflation, and sometimes also the dark gravity that we attribute to dark matter. Any progress, or do you watch those things?
Yeah, so the question was about whether there are alternative gravity theories which might explain what we think is dark matter, but they would explain it purely in terms of a difference in the laws of gravity. So there are many such ideas that have been put forward. As yet, none of them are particularly successful, I would say. They're able to explain some phenomena, but in general, they're not able to explain everything we know about dark matter and galaxies and the structure of the universe. But those ideas are still out there, still being put forward, still being tested. It's just that right now, dark matter is the most convincing explanation for the whole collection of phenomena that we see.
Well, I'd like you to please join me in thanking everybody.
Thank you.
Working all the time.